Hi everyone, my name is Kyleigh Quillian, and this is my Lab 3 presentation titled Black Hole in Orbits. In this experiment, I used GlowScript to simulate a star orbiting a black hole and later a spaceship orbiting both a planet and a moon. This lab connects Newton's second law and momentum to gravitational motion in orbiting systems. This lab was divided into two parts. In part 1, I analyzed the motion of a star to determine the mass of an unknown black hole. In part 2, I used that information to determine an initial velocity that would allow a spaceship to orbit near the black hole, or in this case, a planet and a moon without crashing. Overall, the goal was to see how Newton's second law applies to orbital motion and how momentum changes under gravitational forces. The key physics behind this experiment came from Newton's second law and the law of universal gravitation. Newton's second law states that the net force of an object equals the rate of change of its momentum. The gravitational force equation describes how massive objects attract each other. By combining these, I could calculate the black hole's mass from the motion of the orbiting star. Using the GlowScript model, I generated a unique orbit by entering my Georgia Tech email address as a seed. The code calculated the star's position, velocity, and momentum at every step. I then determined the change's momentum over time, which gave me the net force acting on the star. Using the gravitational equation, I rearranged to solve for the black hole's mass. The printed values for MBH varied slightly throughout the simulation, so I averaged them to get one final estimate. This is the video to the simulation results for part 1. The animation shows the star's elliptical orbit around the black hole, as well as the net force vectors changing in both direction and magnitude as the star moves. These results visually confirm that gravitational force points towards the center of mass constantly changing direction, which keeps the star in orbit rather than flying off in a straight line. For part 2, the goal was to create a stable figure-8 orbit around a planet and its moon. The setup included a stationary planet at the origin, a moving moon orbiting the planet, and a spaceship starting on the moon's surface. I had to determine the correct initial velocity that would let the spaceship loop around both the planet and the moon without crashing into each other. The same physics apply here. Newton's second law and universal gravitation. I calculated all gravitational forces acting on both the moon and the spaceship. Then I added them together to find the net force of each object. Using F equals ma, I found acceleration and then updated velocity and position at each time step. This process predicts how the spaceship and moon move over time. In this simulation, I adjusted the spaceship's initial velocity through trial and error until I found one that allowed the spaceship's path to be influenced by both the planet and the moon. The goal wasn't a perfect orbit, it was to create motion where both gravitational pulls mattered. The resulting trajectory showed the ship weaving between the two bodies in a figure-8 pattern. This video shows the results for part 2. The moon continues orbiting the planet in a circular path, while the spaceship follows the looping orbit that interacts with both gravitational fields. The motion shows how small changes in initial velocity can completely change whether the ship crashes, escapes, or maintains orbit. Since this was a computer simulation, there are a few possible sources of error. The model assumes there are no outside forces besides gravity. Trial and error was used to find initial velocities, which might not be the most precise method. Because it's a simplified system, it doesn't perfectly represent real orbital dynamics or the influence of other bodies. Still, though, it provides a strong conceptual understanding of how gravitational interactions shape motions. This lab demonstrates how the net force and the rate of change of momentum describe the same physical effect, the star's motion under gravity. The parallel component of the force changes the speed, while the perpendicular component changes direction, resulting in curved motion. Overall, this shows that Newton's second law applies directly to orbital paths. Force and momentum are two ways of describing the same relationship between motion and gravity. If we expanded this model to include all objects, the black hole, star, planet, moon, and spaceship, we need to include every gravitational interaction among them. The black hole's gravity would dominate the system, but the smaller objects would still exert small effects on one another. Predicting the entire system would mean constantly updating every object's position and velocity using Newton's second law to account for all those interactions. In conclusion, this lab showed how motion, momentum, and force are deeply connected through Newton's second law. By simulating both a star-black hole system and a planet-moon spaceship system, I was able to visualize how gravity creates orbits and how small changes in velocity can dramatically alter motion. These principles apply everywhere, from satellites around Earth to stars orbiting black holes and galaxies.